In this tutorial, we have a reactor with 2 inlets and 1 outlet. Methane stream enters at a temperature of 25 degrees Celsius, a pressure of 2 bars, and a molar flow rate of 100 kmol per hour. This stream contains 100% pure methane. Second feed stream is air. Air enters at a temperature of 25 degrees Celsius, a pressure of 2 bars, and a molar flow rate of 260 kmol per hour. This stream contains 79% nitrogen and 21% oxygen. Methane and oxygen are reactants, and they react to form carbon dioxide, carbon monoxide, and hydrogen gas. The conversion of first reaction is 40% and of second reaction is 60%. The outlet stream is product stream whose flow rate and composition needs to be determined. Now, we will model this whole process flow diagram in Aspen HYSYS. There are different reactor modules available in Aspen HYSYS. There are 2 modules based on the balance, that is yield swift reactor and conversion reactor. There are also 2 modules based on the equilibrium, that is, equilibrium reactor and Gibbs reactor. And 2 modules based on the kinetics, that is plug flow reactor and CSTR. We will be using conversion module for this case. Because conversion reactor is used when reaction stoichiometry and conversion or molar extent for each reaction is known. Reaction kinetics are unknown or unimportant. There is no need for thermodynamic expertise for this kind of reaction. PFRs and CSTRs can't be used with conversion reactions. In a reaction set, conversion reactions cannot be grouped with any other type of reaction. Specific reactor operations can only support one particular reaction type. For example, if we try to add equilibrium reaction to already existing conversion reaction set, we will get an error. Open Aspen HYSYS software. Click on New button. Click Add to open the component list. Add pure components by typing their names in the search bar and pressing Enter. Enter C1 for methane, O2 for oxygen, N2 for nitrogen, CO for carbon monoxide, CO2 for carbon dioxide, and H2 for hydrogen. Go to Fluid Package, click Add, scroll through the list, and select Pung-Robinson as the property package. In the navigation pane, open the Reactions tab and click Add to create a new reaction set. Again, click on Reactions tab and rename Set 1 to Oxidation. Double-click the oxidation set and click Add Reaction. Create 2 conversion reactions, then close the window. Double-click on Reaction 1 to add its details. First, enter all the participating reaction components, and then define their stoichiometric coefficients. Define coefficients of reactants with negative sign and products with positive sign. Set the conversion to 40%, then close the window. Repeat same procedure for reaction 2. Double-click on reaction 2 to add its details. First, enter all the participating reaction components, and then define their stoichiometric coefficients. Set the conversion to 60%, then close the window. Click on Rankings button to make the reactions operate sequentially. Assign 0 rank to reaction 1 and rank 1 to reaction 2. This ensures reaction 1 occurs before reaction 2. Close the Rankings window. Now, click on Add to FP button to attach reaction set to Fluid Package. Now, proceed to the simulation environment and begin developing the process flow diagram. Add 2 material stream by dragging the blue arrow from the object palette. Double-click the stream 1 to enter its properties and name it methane. Set the temperature to 25 degrees Celsius, the pressure to 2 bars, and molar flow rate to 100 kilograms mole per hour. Next, open the Composition tab and enter the mole fraction of methane as 1. After defining the composition, click OK and close the methane stream window. Double-click the stream 2 to enter its properties and name it air. Set the temperature to 25 degrees Celsius, the pressure to 2 bars, and molar flow rate to 260 kilograms mole per hour. Next, open the Composition tab and enter 0.79 mole fraction for nitrogen and 0.21 mole fraction for oxygen. After defining the composition, click OK and close the Airstream window. Now, open the Object palette and select General Reactors. After clicking it, a new palette appears showing different models. From these models, choose the Conversion Reactor. Finally, insert the selected reactor into the process flow diagram by placing it in the desired location. Double-click the reactor icon to open its window. In the inlet field, select air and methane streams. In vapor outlet field, enter oxidized vapors to create a new material stream. Although the liquid product from this reactor will be 0, you must still assign a name to the stream. In liquid outlet field, enter oxidized liquid to create a new material stream. On the Details page of the Reactions tab, select Oxidation as the reaction set. This selection automatically connects the proper reactions to the reactor. Select Worksheet tab. Green status bar confirms that the reactor is fully defined and results are available. Go to the Composition page and analyze the composition in vapor stream. In a reaction set, conversion reactions cannot be grouped with any other type of reaction. So, for adding equilibrium reaction, we have to define another reaction set. Go to the Properties environment and select Reaction tab. Click on Add button to add new reaction set. Select Add Reaction and add equilibrium reaction. Define the reaction and add it to the existing fluid package. Then go to the Simulation environment and double-click on Conversion Reaction. Go to the Reaction tab. You will not be able to add equilibrium reaction set to the conversion module. Now, drag equilibrium reactor for equilibrium reaction. Double-click on this icon, go to the Reaction tab, and now you can add equilibrium reaction. Soon, I will upload detailed video on modeling on equilibrium reactor.